Well, hello physics students, welcome back. So in this video, we are going to talk about electric potential some more and derive the Ed equation. Do you remember the famous Mr. Ed? All right, so here we are with our good old parallel plates with the positive and negative charge densities, equal and opposite charge densities on the plates. And we just have points A and point B marked off on here. And we're given that the change in voltage or change in electric potential from A to B is some number, we will call it V naught. Okay. So how does doubling the electric field strength from doubling the electric field strength change the change in voltage from A to B? So this is a question that we are going to answer in this video. All right. The other question we're going to answer is, how does moving A and B closer to each other within the same original scenario affect the change in voltage from A to B? So, in other words, how do we find the change in voltage given the electric field and the distance between the points A and B? All right, so let's go back to our scenario that we love. We have this positively charged object right here at A, and we are going to use an external force, Rand the hand, pushing it all the way to B right here. And it moves the distance D completely against the electric field in this case. Okay, so we know that the work is equal to the change in potential energy plus the change in kinetic energy. Well, if we start and end from rest, the change in kinetic energy is 0, so we only have to worry about the change in potential energy. Now, remember that the change in electric potential energy is equal to the charge, the test charge, times the change in electric potential from A to B. All right. Also, recall that work is equal to a force times, we used to write it, or we can still write it, as F change in X. But instead of change in X, we just call it D in this case. Okay. What is the external force? Well, it's the force. Well, let's look at a free body diagram first. So we have an electric force pushing the charge one way and Rand the hand pushing the charge the other way with an acceleration of 0. So the force is equal to the electric force, which is equal to the test charge times the electric field, QE. That D stays there in the equation, and the Q test times change in electric potential still on the other side of the equation. Q tests cancel out. So we're given this equation. Change in voltage from A to B is equal to the electric field times the distance. Now, big caveat here. This is only true for constant electric fields, which in our case, it's only in between these parallel plates. Now for us, this happens a lot, and in real life, this happens a lot. Capacitors are very prevalent, and it's good to know this. It's not this special case that never shows up. It shows up a lot. But, and for us, in honors physics, we will only look at this case. If you go on to take AP Physics E&M, then you will have to realize that you could only use this equation for constant electric fields. So it's one of the very few equations that are very particular and only holds for a very particular case. But for us, ooh, welcome to my clock. So this holds true. Okay, so in the next video, we will work out some examples with this.